reaction to occur according to the Nernst equation. It's a negative delta G, positive E value. So let's try an example. Okay, so we have iron metal reducing nickel. Okay, so here's my favorite word. So we have iron reducing metal. So it's very important that when you read these, you make sure you know what species is doing what. So we have iron and we have nickel. So we've got iron and we've got nickel. So which one's being reduced? So we want iron to reduce nickel. So here we've got reduction going on. Okay? The iron therefore has to be oxidized. So which of these equations are we going to flip? You have 50-50 shot.
Yes.
Okay. I heard somebody finally say it, I think. Okay? All right. So what are the values? I can see it better here. Nickel is reduced as negative 0.26. Is that right?
We have a choice for iron.
Oh, we do have a choice for iron? Let's do both.
Yeah, there's two different ones.
Where are they? We've got one that's +2, right? So we've got the iron +2, which is negative 0.45. And we've got the iron, which is, what's the other one?
You might not be able to.
3 plus, which is 0.77. Okay. We can already kind of see what's going to happen, right? One of the irons going to give us a spontaneous reaction? Is one going to give us a non-spontaneous reaction? Yes. Okay. So what we need to do, we know that is the nickel. We don't have another one for nickel, do we? No. Okay. So nickel stays the same. So let's do. Here's iron 2, and here's using iron 3. So we've got negative 0.26. Do we keep that one or change the nickel? Reduction. Keep it or flip it?
Keep it.
Keep it. The other two we have to
Subtract.
flip or subtract, yeah. So for the iron 2, what do? Negative 0.45 becomes positive 0.45, and you can add those together, who cares? And the iron 3 plus becomes what? Negative 0.77. So overall here, negative plus a negative is what? Negative whatever that is. Positive minus 0.26 is going to be positive. So if we plug that value in, first of all, we have to look at how many electrons they each transfer. How many electrons does nickel transfer? 2. This iron only transfers 1, and this iron transfers 2. Okay? So you actually have to take that into account. Here's the other thing. In biochemical systems, though, the different reactions happen one after the other. For example, cytochrome C is a 1-electron system. It takes the reactions over one at a time. So you actually have 2 of these reactions going on. That's kind of different than what you do in PCAM. Okay? So what you actually have to do in biochemistry, if we were dealing with something where the iron had to do the same thing twice, okay, for the 1-electron system, you would multiply it by 2. Which one is that? Is that a 3 or is that the 3?
Yep.
The 3? So the 3 one, you actually have to multiply this value by 2. Okay? That's a little bit different than we see in PCAM. But we'll see where that happens when we get to the electron transport chain. Okay? But does that really change the fact that this is going to be a non-spontaneous reaction? No. And then what you do is you take the number of moles of electrons, in this case each of them are 2, right? You take it by times Faraday's constant, right? And then you multiply it by whatever those values are to give you your delta G to the Nernst equation. Okay? Yeah,
I think it's the Fe2 that gives 2 electrons when I take it.
oh, it is? Fe2 only has 1?
Because it goes from Fe2 to Fe solid.
Yeah.
And Fe3 goes to +2.
Yeah.
Did I do it wrong?
Well, no, you did. The arrow could only go to the Fe2 plus.
The arrow what? Sorry?
That you drew from
Yep.
2 times Faraday's constant. You can only go to the Fe2 plus.
The 2
The one
electrons.
that's doing the 2 electrons.
Right, but this one is now doing 2 if you multiply it by 2. Yeah. So does that answer your question, Ben?
Oh, okay.
So we're looking, I still want to answer your question using an example that we haven't gotten to yet, but I will. It's different than if you do it in PChem and other things. But for example, if you have an enzyme that has an iron 3 plus, and it has to transfer 2 electrons because it got 2 from like coenzyme Q or something like this. You have 2 it has to do it 2 at a time. Because it does it 2 at a time, you actually get this value times 2. Right? Does that clarify a little bit?
Yeah, and then how do we know that we need to flip the iron one?
Which one? So yeah, because since iron is being oxidized, these are all in reduction potentials, so the oxidation is just flipping them to go the other way. Yeah. So you're actually taking this and flipping it back that way.
Okay.
Does that help?
Yeah.
So I'm not going to do the other one. There's another one that you guys can do. If you have questions, let me know. But let's talk about how we change this and look at the free energies, right? Remember the delta G tells us about how spontaneous a reaction is. So again, the larger the redox potential, the more negative the delta G is, right? Okay, so if you had to pick, let's go back here to this chart. So let's say, so here we've got, so what's the best reduction agent, best reduced fluorine here? If we wanted to get the highest E value that's positive, what would we couple that to? Lithium. That would give us the overall biggest delta G that's on this table, right? That would give us the fastest reaction, right? No, remember it doesn't tell you about the reaction. But the larger the delta G values, the more things that you can use to, I erased it. Magic word, when you have positive delta G, you can use it to couple. So that reaction could couple to more reactions that have a positive delta G than other reactions. Okay, so the larger the number, the higher the redox potential, right? It's not, again, more or less spontaneous, but that's the energy that drives a potential reaction. Kind of like, again, phosphoenol pyruvate versus glucose 6-phosphate. One can couple to more reactions to drive those than another one, okay? And that's the important thing, is that the metals and the redox centers that we use in our bodies are there specifically because they provide the certain delta G value to drive certain reactions, but not other reactions due to the amount that there is. Again, it doesn't tell you about how fast it happens. It just tells you, hey, I've got enough energy to drive reactions A, B, and C because they're all less than 20 kilojoules. But I've got enough energy to drive all of those reactions because they're all, less than 60 or whatever it is. Okay? Here's what you will be given on the next exam. So please don't worry about memorizing this table. This is a table from your book, from chapter 14. This gives you a lot of sets of biochemically important half reactions. Again, these are some of them. If we had a table that had all of them, it would take up a lot more space. Okay? I will give you Faraday's constant. Okay? So, if you notice, what do we inhale to use in our bodies again as kind of fuel? Okay, look up here. What is this? Oxygen. What do you notice about its redox capabilities? What do we think on this? It's the highest. Okay, so you think redox chemistry comes into play, and the fact that we use oxygen is probably a good thing? Yeah. And we see some of these other reactions. We haven't seen a lot of them yet, but we will. Like, we've heard of cytochromes, right? Yeah. Cytochrome C and left. Cytochromes transfer electrons. Okay. Pyruvate, acetaldehyde, FAD, NAD+, NADH. What do you notice about NADH? Making NADH, is that favorable? Not really, but if you turn it back to NAD+ and give up those electrons to something else, that turns that positive to negative overall delta G when coupled with something else. Okay, so if you put those largest two pieces together, you get something very, very big, which can drive a lot of reactions. Okay? Should we try one of these?
Yes.
Yeah? Okay. Should we try which one do you want to try? I got 3 up there. Which one do you want to do? You want to do the NADH with the oxygen, which is the ultimate one that we talk about?
Of course.
Sure? Okay. So, all right, so you guys tell me what to do. So we've got here NADH being oxidized, and we've got O2 being reduced, okay? So what do we do about our O2 up top? Nothing. So we keep that number the same, which is what? 0.815. Positive or negative? Positive, all right? Now we're going to take NADH and change it back over to what? You're going to oxidize it to, so is this the reduced or oxidized form? So we want to oxidize it to NAD+, which means if you look on this chart here, are we keeping this reaction this way, or are we going the opposite way? Opposite. So what do we do with this number? Flip it to what? Positive 0.315. Everybody okay with that? Yep? We okay with that? So this value is what in our Nernst equation? This is our E. Is it positive or negative?
Positive.
Positive, okay? So our delta G equals what? Negative. How many N's? So what's our N value here? So how many electrons in that up top here? How many electrons? 2. How many down here?
2.
So our N value is? Do we need to multiply by anything? No. So we've got 2 times Faraday's constant. Now, this is in joules per volt per mole. You can also put 96.485 if you do kilojoules. Do I care which one you do? But if you have this in joules and this is in kilojoules, are you wrong? Yes, so make sure your units are consistent. And our E value, 1.13. Okay?
Questions?
Yeah.
Can you explain me how you get the number of electrons?
Yes, so it comes from how many are transferred. So if you notice, here we have 2 electrons that have to go on there to get water. So we've got basically just this number here. So if you notice, the cytochromes mostly do 1. Most of the other ones just do 2. So you would look that up on the table. Yeah.
And you're looking at which one is doing the reduction, or which one is reduced? You're taking that number of electrons, or the one that's oxidized?
They have to equal, right? So they have to cancel because if you take 2 electrons from something else, it's got to 2 have to go to another thing. So they have. So if you were to couple cytochrome B with acetaldehyde, you'd have to multiply this by 2 because it does it twice. Yeah. Does that answer your question? All right. Anybody have a calculator? Do that quick. So somebody do that really quick. The main thing is that so what do you think you're going to get for your value here? Negative or positive delta G? Negative. A negative delta G value, right? And this value, 1.13, right, we took a value that was pretty high up here and pretty low down here. So this is going to be one of the ones that's going to give us, what do you think, for a delta G value? Pretty big, okay? Remember, we use NAD plus a lot, and we use oxygen a lot, and these are the reasons why. Oxygen oftentimes is called the ultimate electron sink because it has such a high affinity for those electrons, right? Its reduction potential is pretty much the highest on this chart here. That's not a coincidence, okay? Anybody get this number?
218,056
joules. So if we turn that into kilojoules, 218 kilojoules. Now, if you think about this, negative 218, how many kilojoules per mole does it take to make an ATP? 30. So if we want to figure out, well, how many ATPs can we make from this, we would divide this by 30, okay? Anybody know what that gives us?
7.
About 7, okay? Doing glycolysis Krebs cycle electron transport chain gives us like almost 40. Gives us 38, 36, 32, depending on how you count. More or less than 7. More. So it's not just the redox that's happening. Okay? Here's the other thing. This last one right here, I want to know, can malate reduce NAD+, yes or no? Okay? So this is actually something that happens in the Krebs cycle. So if we go through, I'm just going to go through the answers, the example really quick. But again, you have your 2 reactions. One of them you flip, one of them you keep, right, based on that. So there's our overall reaction. What do we think? Is it going to happen?
No.
No. Here's the thing, though. It's non-spontaneous, but it does. It happens because, anybody remember what I talked about way at the beginning when I said you could have A, go to B, go to C? You can have subsequent steps which drive the previous one. It's not just based on the metal that's there, it's based on all the other pieces that come down, okay, with it. All right, so we're going to see a lot of NADHs, FADH2s, especially when we get to the Krebs cycle, okay? So next week on Monday, we're going to start glycolysis, okay, so chapter 15. If you have questions, I would highly suggest doing some more practice with the redox chemistry. Again, on the exam, I will give you this chart, but you need to be able to interpret that.